Everybody, my name is Kamau Kingora, and today I'm going to be talking to you about numerical simulation of mass transfer from multiple cylinders. My talk is divided into these sections, and we are going to start with the introduction. So there are various engineering applications that can be modeled as flow over multiple bodies, starting from closed for heat exchangers to cooling towers, among others. So in literature, many people have studied the effect of changing a gap ratio for two side-by-side as well as inline cylinders, but there are very few studies that focus on more than two cylinders, both inline and side-by-side. As a result, the effect of adding a cylinder on an existing structure at a specific gap ratio and Reynolds number is not really that well established, and even fewer studies focus on heat and mass transfer on structures with more than two cylinders. In this study, we hope to study the mass transfer over multiple cylinder, both the inline and side by side, and to study the effect of an additional cylinder on an existing structure at a specific gap ratio and Reynolds number, and see exactly what is the effect of adding a cylinder on an existing structure insofar as flow physics and mass transfer is concerned. So the results presented in this study are performed through immersed boundary method. And immersed boundary method, you have a very simple Cartesian mesh and you have the object and you just map both of them together and run the simulation. This is very attractive because you can run very complex geometries on a very simple Cartesian grid. So there are various immersed boundary method. We have the diffuse interface method, which we are not going to be discussing about in this talk. And we have the sharp interface immersed boundary method. So for sharp interface immersed boundary method, we have first the ghost cell and then the card cell. Now the ghost cell acts enforce the no-slip boundary condition through an action of a ghost cell. And a ghost cell is actually defined as a cell in the solid domain that has at least one neighbor in the fluid domain. And the values of conservative property in this ghost cell are modified so that we enforce the no-slip boundary condition at the interface. The main shortcoming of this method is that it depends on the interpolation, and the accuracy of the method is dictated by the accuracy of the interpolation procedure. So that is not very good, especially because interpolation deteriorates with the increase in the cell aspect ratio. So the other problem is the difficulty in implementing Newman boundary condition, because not every immersed boundary cell has a unique ghost cell. So that becomes a problem because the immersed boundary is not captured consistently from one boundary cell to another. So the other method is actually the cut cell method, and this works by reshaping the shape of the immersed boundary cell to conform to the shape of the boundary, just like conformal grid. And this is known to be the most accurate. However, it suffers from the fact that it's very complicated to implement, and this is because there are very many cell shapes that emanate from the cutting process, and calculating the volume and the areas is actually a very difficult job. So at the time of this recording, we don't actually have an 3D implementation in literature insofar as we as far as we know. The other problem is that it suffers from severe time step restriction, and this is because the very small cells emanate from the cutting process, and the CFL condition dictates that we reduce the time step so that we don't suffer from the instability. So in this study, we are gonna be implementing a new interpolation-free mass boundary method. We call it the hybrid mass boundary method, and this is because it captures the immersed boundary through the strength of both the ghost cell and the cut cell method. And we are gonna be discussing this in the future slide. All right, now our new method starts by domain marking. And this one, if you have a computational domain, so let's say the fluid cell is actually the green region, and the solid region is actually the gray part of the domain. So cells whose center are in one domain are actually marked to be in that particular domain. For this case, the cells with red centers are marked to be the fluid domain, while the cells with blue centers are marked to be in the solid domain. So let's see how the ghost cell method works, and then try and see what we can improve in the ghost cell method. So the first thing in the ghost cell method is to mark the ghost cell, which are this cell with double cycles that has at least one neighbor in the fluid domain. And then the center of those ghost cells are mirrored to the fluid domain, and since we don't have properties at that image point, then the properties at that image point are determined through interpolation of the neighboring fluid cells. And actually that the properties at the image point are then mirrored back to the ghost cell to impose the no slip boundary condition. So the problem is that it relies on interpolation. As you can see, it relies on interpolation, the accuracy, whose accuracy actually depends on the cell aspect ratio. And the other thing is that there are some cells that don't have a ghost cell, and that is a problem because the immersed boundary is not captured consistently from one immersed boundary cell to another. And the other thing is that we have interdependence between ghost cells, which actually deteriorates the accuracy. All right, let's see how let's see how our procedure is a little bit different from that of the ghost cell. Now, after we mark the domain, we actually mark all the cells that have at least two faces to be immersed boundary cells. So in this case, we have and form a virtual ghost cell around them. So in this case, we actually mark these cells as immersed boundary cells. After we do that, we mirror the center of the immersed boundary cell into the opposite domain, and we reconstruct a virtual ghost cell around those centers. Then we actually impose the boundary condition through action of that new virtual ghost cell. So the main score is that interpolation is eliminated, and the reason is because since the immersed boundary cell and the center of the immersed boundary cell and the center of the virtual ghost cell are mirror image of each other, we don't need interpolation since we have the value of conservative property already in the center of the immersed boundary cell. The other thing is that since every immersed boundary cell has a unique virtual ghost cell, the immersed boundary is represented continuously and consistently from one immersed boundary cell to another. So those are the scores of this new image. So let's see how we have a cut cell treatment in this new immersed boundary method. So let's say we have cell which is occupied by two faces. So along the interface, we cut that cell and demarcate the portion that is occupied by one face from the other, from the portion that is occupied by the other. And the portion occupying the center of the cell is actually taken to be the only occupant of that cell. Then the other chunk is actually, and that is actually named as a cell splitting. So we have the mass boundary cell being split in this fashion. The next procedure is actually cell merging, and cell merging, we have the smaller portion of the cell being added to the neighboring cell that is in the same phase as itself, so that we have actually a bigger cell. Instead of having a smaller cells from the cutting process, we merge it to form an even bigger cell. That way we can actually eliminate the time step restriction, as you can see in this figure. So instead of very small cell, we have some very big cells. So the cause of this is that the time step restriction from the car cell method is eliminated, and also the immersed boundary coincide with the shape of the cell. So in that way, we have a very accurate imposition of the boundary conditions. And on top of that, it's very easy to model jump condition, especially in something like multi-phase flow or compressible flow, because each cell is actually occupied by only one phase. So the first thing we do is to check the convergence of our method and check the order of accuracy. And to do this, we implement two cases. The first case is a flat plate oscillating in a cavity. And we do this with a systematically defined mesh, and we calculate error in each mesh and see what is the order of convergence. And actually for this case, we see that where nx and ny are actually order of convergence of u and v respectively, we find that for all time, the method actually converges with second order accuracy. The second convergence study we are going to carry is a sphere oscillating in a cavity, and this is to ensure that our method is actually converging with at least second order, even for complex boundary conditions with curved surfaces, for complex shapes with curved surfaces. And we still do the same thing. We take a sphere in a cavity and we oscillate it and calculate the the error in each mesh, and we can also see that for all velocities it converges with second order accuracy. So the next thing we do is the validation, and in the validation we run some cases that are already established in literature and we check the result vis-a-vis them. And the first case we are gonna take is 3 side-by-side cylinder at Reynolds number 90, and we have a separation, a gap ratio of 4. So the center to center distance between any two neighboring cylinders is actually 4 diameters. And this case was done by PIV by Solage et al. In 2019, and he actually published the time average velocity profile at various points. So we are going to be comparing the profile predicted by this method with what with what he published. And we can see that the profile that is predicted by this method actually agrees very well with the PIV results. So we can say that our method is capable of simulating flow with multiple immersed boundaries. The second validation case, we are going to be doing forced convection of isothermal cylinder, and this is because we want to make sure that our numerical method is capable of simulating flow with heat and mass transfer. And since we don't have any study in literature that actually focuses on mass transfer, so we simulate flow over isothermal cylinder, forced convection over isothermal cylinder, and this is because the mechanism of heat transfer for passive scalar is the same as the mechanism of mass transfer. So if it is good for forced convection, it's definitely good for mass transfer. And we follow the study of Eckert in 1952, who did the forced convection over a cylinder at various Reynolds number, and he published the Nusselt number along the surface of the cylinder. And we can see that the profile actually of Nusselt number predicted by this method are actually in very good agreement with the experimental results. So we can say that this method is capable of solving flow with heat and mass transfer. So in this case, we analyze the flow of an isolated cylinder, and the reason is that we want to compare the flow structures we obtain from this case with the structures that we obtain from multiple cylinder. So for the first movie we have a periodic vortex shading, and for the second movie, the lambda 2 criterion, actually lambda 2 demarcates the section of the flow that are occupied by the swirling flow versus the ones that are occupied by the shearing flow, and the blue region in this figure are actually occupied by the swirling flow, while the red region are actually occupied by the shearing flow. And we also analyze the stresses, the streamwise stresses. These are just the Reynolds stresses, so you can see at which part of the flow we have the highest Reynolds stresses. Then the other thing we also analyze is the pressure along the cylinder. And for isolated cylinder, we can see that the pressure profile predicted by the current model is actually very accurate compared to the published result, especially the experimental result by Hamann in 1936, and the one by Ragini, the numerical simulation of Ragini in 2009. All right. So in this slide, we see the mass transfer characteristic of an isolated cylinder, and we see that the mass is being transported in lumps that maps actually onto the position of vortices. So we can say that actually the mass is being convected downstream, and the time average scalar concentration shows that we have actually higher concentration in the wake region, and which is expected, while actually in the far downstream we have almost zero concentration. So the profile of Choud number along the surface of the cylinder, it shows that we have actually point of inflection, and this actually coincide with the points at which the swirling flow meets the shearing flow. Side-by-side cylinders in closed flow. First, let's examine what happens when the gap ratio is very, very small and we just increase the number of cylinders. So for this one, we are going to have a gap ratio of 1.05. So the difference between the center to center distance between the cylinder is 1.05 diameters. And for that one, we simulate two 3 and 4, 2, 3, 4, and 5 cylinders. And we can see that the flow structure, they really behave like a single body, and there is really not much difference as you increase the number of cylinders. There is really not much difference as you increase the number of cylinders. Then we are going to increase the gap ratio to about 1.5 in what we call asymmetrical biased flow regime. And we find now there is actually, so every cylinder is behaving pretty independently. It is not really a single body, but there is a very huge interaction between the cylinders. And we find that there is actually a deflection. There is a deflection of the wake. All along, there is a deflection of the wake towards one side or the other. So that is actually a symmetrical based flow regime. And then if we look at the symmetrically based flow regime, we find that we have the wake that is deflected almost equally. It's deflected almost equally in both sides. And that is actually true as you increase the number of cylinders in the configuration. Finally, if you put a very high gap ratio, like the gap ratio of 4, we find that the cylinders behave pretty independently. There is really minimal interaction of vortices as they are being convected downstream. So we call that kind of a regime unbiased flow regime. Please look at the mass transfer characteristic of these regimes. So for a single body regime, we can find that the concentration lamps are actually convected in similar manner as the vortices. So we can actually say the mode of mass transfer here is convection, because we have concentration lamps that maps directly on the saturation point of the vortices. And we actually find a very good symmetric. If we look at the time average scalar concentration, we find a very symmetric wake that is symmetric in both upper and lower side of the computational domain of the structure, I mean. So there is no meaningful average velocity in the downstream, which actually makes sense, because as the lamps are convected downstream, we expect them to interact more with the free stream stream, which actually dilutes their concentration significantly. So for this one, we can conclude that the change in scalar pattern due to the size of structure is not so much, is actually negligible. So we don't have really a lot of changes due to the size of this, that is the structure. So let's go to the flow structures. And the flow structures, we find that there is actually a single vortex street downstream, and that single vortex streak resembles that of the isolated cylinder, but we have a difference in that we have base bleeding. If you look at the wake is not really attached to the cylinders, and that effect is actually known as the wake bleeding. So the wake is just symmetrical for all configuration, and if you examine the Stroud number, you find actually that as you increase the number of cylinders, then the Stroud numbers reduces. So that is actually an interesting finding. That is because as you increase the number of cylinders, huge vortices are shed that are more energetic, but at a much lower frequency. So the Stroud number will actually reduce as you increase the number of cylinders in the domain. And similarly for the coefficient of drag. So this is actually just the pressure component. The friction component does not really is not really that significant. As you can see, it is about 20% of the total drag. So if we focus just on the pressure drag, we find that as you increase the number of cylinders in the domain, the drag also increases. And one more finding is that as you move from the outside deeper into the configuration, the dragging experiences by the member also reduces. So in fact, flow structures, we can say they don't depend really on so qualitatively, they don't depend on the number of cylinders in the configuration. But for the forces, they actually do. And the more the number of cylinders in the configuration, the higher the drag forces that they experience. And the deeper you move into the configuration, the more the drag force that you are going to experience. For the Stroud number, you find that the Stroud number that is experienced in this regime is always lower than that of an isolated cylinder, which is 5.6 for this regime, for isolated cylinder at this Reynolds number. So let's go to the asymmetrical based flow regime at gap ratio of 1.5. And for this case, we find that we have a very high interaction between vortices of neighboring cylinders. And instead of the convection that was dominant in the single body flow regime, now we have entrainment at the edge of the wake. So we have a lot of entrainment at the edge of the wake, as you can see in the instantaneous vortices. And then the mass transfer is pretty poor. So in the previous regime, we found that we didn't have a lot of concentration downstream, far downstream, but here actually we have a lot of concentration even far downstream, meaning that the mass transfer is actually poor, which is actually as a result of entrainment as opposed to convection. The other thing we notice is that the convection, so the transport is not really parallel to the streamwise flow. We actually have a wake that is at a specific angle to the flow. So if we look at the symmetrical based flow regime at the gap ratio of 2, now we find that the wake is no longer deflected toward one side, but is deflected towards both sides equally. So if you look at this figure here for both instantaneous as well as the time average scalar concentration, you find that the middle cylinder has a wide wake, and both of them are deflected almost equally toward the lower and the upper side of the domain. So this one is actually called a symmetrical based flow regime because the wakes are deflected equally towards either side of the structure. So at the mass transfer characteristic, at the flow structures of this regime, these two regimes, and we find that for asymmetric based flow, as we have discussed, we have one that has a wide wake and another one and one side that have a smaller wake. So for the two side by side cylinders, we have the upper part actually have a wide wake, but the lower cylinder has actually a pretty smaller wake, and that goes for all the members of configuration. You find that you have one side that it has larger wakes and another side that have smaller wakes. So we have a deflected wake. For symmetric based flow regime, as you can see in the second column, we have both cylinders in the configuration for two side by side cylinders having almost equal wake, but both of them deflected towards the outer cylinder. And actually that goes even for side by side cylinder having now a very wide wake in the middle because it is deflected equally toward the upper and the lower side. And that is also true as you increase the number of cylinders in the configuration. One thing we also notice is that the phenomenon in the first phenomenon that we realized in the single body flow regime, that the drag coefficient, the drag increases as you increase the number of cylinders in the configuration, is also true for this regime. And we can also see also as you move deeper into the structure, then the drag also increases, which we also discussed in the single body flow regime. One thing that is actually different from the single body flow regime is that the Stroud number is no longer uniform for all configuration, and it is actually much higher than the Stroud number of a single cylinder. So the Stroud number is actually much higher. The reason being that now the inner shear area is actually developing and shading vortices, but there is a lot of interaction in the downstream. So we find a uniform wake downstream, but the frequency is actually high, like that one of a single cylinder. So the mass transfer coefficient, or the Stroud number, we find it is actually comparable to the single cylinder. We have 5.8 in most cases, 5.8, 5.9, and for the single cylinder is about 5.6. So we can say that the mass transfer coefficient is actually. Finally, for the side-by-side cylinder, we have unbiased flow regime, and unbiased flow regime is actually having a very large separation such that the interaction between vortices of neighboring cylinder is very minimal. So as we can see that the scalar concentration are transported almost parallel to the flow, pretty much parallel to the flow, and actually we can see that there is really minimal interaction between the scalar between the scalar from different sides. So you can see even far downstream we can tell which vortex was shaded by which cylinder. Okay, and that phenomena actually is consistent as you increase the number of cylinders in the configuration. So let's add the forces and the other flow structures. So we find that the forces are actually still high. They still maintain the same pattern of higher number of cylinders having larger drag force, and that means that obstruction is still there. We don't have a complete decoupling yet, and some people think that actually you won't have a complete decoupling until about S over D ratio of about 7.9. So we still have minimal interaction. That is why the forces are actually a little bit higher than that of a single cylinder. But on the other hand, the Stroud number really resembles that of a single cylinder. We have it about 5.6 for all members in the cylinder, which means that insofar as mass transfer is concerned, we are almost fully decoupled, because the mass transfer decouples before the flow structures. So a single vortex street is actually observed behind every member for at this flow regime. So let's actually the inline cylinders and see how they fare on. So for the inline cylinders, so if we look at a small gap ratio, now we have a different phenomenon. In side-by-side cylinder, we have them behaving as the same as a single body, but a single body that is actually a little bit like elongated. So for this one, we have the same phenomena, but in different direction. So if you have a gap ratio of 1.05, the body behaves like an extended body. So the shear layer from the inlines from the upstream cylinder encrosses the the downstream cylinder, making it behave like an elongated body. And you find that the effect of the number of cylinders is now significant. As you increase the number of cylinders, then you find that the flow become more stable, shed the vortices much slower. And finally, actually, when this number of cylinders is 4, we find that we have a really stationary flow. We don't have any vortex shading going on. So if we increase the gap ratio to 1.5, then we have reattachment. So the shear layer from the upstream cylinder reattaches onto the surface of the downstream cylinder. So it no longer behaves like an extended flow, an extended body, but we have a cavity-like flow in between the cylinder, and that goes for all as we increase the number of cylinders in the configuration. But as we increase the number of cylinders in the configuration, the vortex shading behind the rear cylinder actually becomes less frequent and finally stops. When we have 3 and 4 cylinders, we find that we actually don't have any vortex shading, any noticeable vortex shading downstream. So we find that the effect of adding number of cylinders is actually stabilizing for this low this low gap ratio flow rate. And another noticeable feature is that vortex shading is only occurs behind the trailing cylinder. So if we look at the gap ratio of about 4, as we increase the gap ratio, we find that now we have a shear layer that is attaching momentarily onto the surface of the other cylinder. So we have a shear layer that goes and attaches the other cylinder, but is momentarily disrupted because there is a noticeable development of vortices from the upstream cylinder. In most cases, we find that the vortices from the upstream cylinder, they develop, but they don't shade. They strike the downstream cylinder before they shade. But as we increase the number of cylinders in the configuration, we find that the vortices from the upstream cylinder act like they are washing away the vortices from the downstream cylinder, preventing them from fully developing. And that goes as we increase even the number of cylinders even further. And if we increase the gap ratio even further, then we have the core shading regime, in which all the cylinders in the configuration shade vortices. And we find that in this regime, the only effect of the upstream cylinder on the downstream cylinder is that the downstream cylinder behaves like it is in the periodic flow, such that is being impinged by the vortices from the upstream cylinder, hence shading more energetic vortices. But apart from that, it behaves like an isolated cylinder. Okay. So let's look at the flow characteristic for these ones. And as we can see here, if we look at the flow characteristic, the drag coefficient and the Stroud number, we find that the Stroud number for all the members in the group are the same, and that goes without saying because we have only one vortex shading, which is behind the rear cylinder. But actually, the lift coefficient, the lift force is pretty much negligible in this flow regime for extended body flow regime. Finally, we see that the first cylinder or the leading cylinder experiences the highest drag, not as high as the isolated cylinder though, but it experiences the highest drag. And the second cylinder actually experiences negative drag. This is not a weird finding, it was found a little bit earlier. And this is attributed to the fact that the inner cylinder, the trailing cylinder actually sits right in between the shear layer of the upstream cylinder. So that makes it have a negative drag due to pressure surf. Anyway, so let's see what happens really as we increase the number of cylinders. We saw that the streamlined become closed. We have a closed wake here. So for the first 2x size cylinder, we can actually see that we have a vortex shading. But as we increase the number of cylinders, we find that that actually now diminishes. And actually, by the time we have 4 cylinders, we have a closed wake. We don't no longer have vortex shading. We have a closed wake, like the case of Rolls number. And the time average contours of streamwise velocity shows that we have also a closed wake behind the trailing sphere. So the mass transfer coefficient also behaves the same. We have the extended body. We have actually very high mass transfer from the leading cylinder, but actually as you move along but as you go downstream, you find that the mass transfer is not as great. This is because actually we have very minimal mass transfer from the trailing cylinder. So let's increase now the gap ratio to about 2, and we find out in the reattachment flow regime. Now in the reattachment flow regime, we don't really have stationary flow in between the cylinder, but we have the flow behaving like a cavity flow. In between the cylinder, we have a cavity kind of a flow. And we see that even for this case, as we increase the number of cylinders, the wake stabilizes and we have a closed wake. And similar for the and similar phenomenon is observed for the trailing cylinder. We have a closed wake from the number of cylinder equals from n equals to 3 to n equals to 5. And that is actually the same phenomena. So the coefficient of drag still behaves the same. We have the leading cylinder having the highest drag, and then we find the second cylinder actually have negative drag, and then drag increases as we go along. One of the noticeable feature insofar as mass transfer is concerned in this regime is that we have significantly higher mass transfer coefficient of the leading cylinder from that of an isolated cylinder. So that's something to notice. And also you can notice that as you move downstream, the mass transfer coefficient diminishes. So as you move downstream, the mass transfer coefficient diminishes in this region. All right. So this is the mass transfer. This is the mass transfer structure for this regime, and actually we find that it is the similar to the flow structure. So we have really not much to discuss here, as we have said that the leading edge, the mass transfer coefficient is much higher than that of the isolated cylinder, and also we find that the structures are actually similar to the vortices, the flow. If we increase the gap ratio to 4, now we have now a disrupted or the bistable flow regime. Now in this flow regime, we have the vortices forming from the vortices from the upstream cylinder forming, but those vortices, they don't shed. They strike the downstream cylinder before they shed. Hence, they mix with the vortices from the downstream cylinder and shed still as one thing. So in most of the cases, you will find that we don't have noticeable shading from the upstream cylinder, but we have actually noticeable shading from the downstream cylinder. And that goes as you increase the number of cylinders in the domain. But now, one of the phenomena that actually emanate in this one, instead of stabilizing the flow which was happening at lower gap ratio, now the instability starts from the downstream cylinder and moves up. So you find that the trailing cylinder are shading, they are co-shading, but actually the upstream cylinder are not shading, they are still actually in what is called the reattachment regime, or the reattachment regime, or in the disrupted regime. So all the cylinders don't behave the same. So the gap between the cylinders, the flow in between the gap between the cylinder is actually different for different configuration. And this is actually the phenomenon that happens as you increase the number of cylinder. And similar thing is observed for the mass ratio. We find that the mass ratio really follows the structure of the flow. And we find that the mass ratio, as you increase the number of cylinders, the mass transfer coefficients also increases, something that we didn't notice in the other flow regimes. So we find that for the leading cylinder, for 2 cylinder, we have about 5.79, and that one increases as you increase the number of cylinder in the configuration. The other things that actually happens is that this is actually opposite to the reattachment regime, is that from the second cylinder, as you move downstream, the mass transfer coefficient actually increases, while the other side it was actually decreasing. But the same thing happens insofar as Stroud number is concerned, because we have this all the members in the structure having the same Stroud number. The reason is because they have one vortex shading frequency, since the vortices from the upstream cylinder comes and actually force this the vortices from the downstream cylinders to shade, forming one large vortex. So that is actually in this flow regime. And for the flow structures, we have actually discussed that. So for the flow structures in the co-shading regime, so if we go to the co-shading regime, for the flow structures, we find that all the cylinders in the configuration are actually now shading. Find that in this regime, all the structure, all the cylinder are shading the vortices, and the effect of the upstream cylinder on the downstream cylinder is that the vortices from the upstream cylinders impinges on the vortices on the surface of the downstream cylinder. Actually, that causes the vortices from the down cylinders to shade prematurely, but all the members now have the same vortex shading frequency. As you can see, the Stroud number is the same for all the members, and we can find that the coefficient of drag is now comparable to the to that of an isolated cylinder, at least for the leading cylinder. But for the other cylinders, the drag is still lower, as the instability starts from the lower side, from the trailing edge, as you approach the leading edge. For the mass transfer, we have the same thing actually, but we can see in this regime that the mass transfer for the leading cylinder is pretty close to that of an isolated cylinder. We have about 5, we have about 6. And actually, the other thing we notice is that we really don't have a specific format in which it behaves. The child number behaves as you move along, and that is because we have shading that actually happening from all the cylinders. So we don't have a very good relationship for mass transfer as we move down the cylinder, and that is it for the. So in conclusion, we can say that we have 4 flow regimes for side-by-side cylinders for a gap ratio of 1.05 to 4 at Reynolds number 90 at least. And those flow regimes, as that for lower regimes, we have the single body flow regime, and then as you increase, you have a deflected wake toward one side, which we call a symmetric burst flow regime. Then we have symmetrical burst flow regime, where we have both we have deflection on both sides with equal angles, and finally we have what we call an independent regime, in where we have all the cylinders behaving independently. Finally, we can say that the drag force increases as the number of cylinder in the configuration increases, and this is true for all the gap ratios. And also it's so that as we move deeper into the structure, the drag force also increases. So the drag force increase experienced by members at different position is actually different depending on the size of the structures. Another thing we noticed is that the lift force is always positive, downward and outward pointed. That means that two neighboring cylinder always experience a repulsive force, which is something that we can say for all gap ratios and all configuration of different members. Insofar as mass transfer is concerned, we say so that most cylinders in the configuration are low gap ratio exhibit Stroud number that is lower than that of isolated cylinder, and that is not really the case for for higher gap ratio, because at that regime all the cylinders have about similar mass transfer coefficient, which is comparable to that of isolated cylinder. For inline cylinder, on the other hand, different flow patterns are realized depending on the number of cylinders in the configuration. So we find that for very low gap ratio, we have extended actually goes to reattachment regime as you increase the gap ratio, and finally we have co-shading regime if the gap ratio is really big. So vortices from the upstream cylinders impinges on the surface of the downstream cylinder, causing them to shade. So in this regime, all the cylinders experience the same Stroud number, and then the leading cylinder is always having the highest mass transfer coefficient, or the Stroud number. So that is it for this talk, ladies and gentlemen. And, that's it. Thank you so much.